Welcome friends. Today we are going to learn about gain margin and phase margin, two of the most demanded topics of frequency domain stability analysis of control systems. So the main points we are going to discuss today are: what is gain crossover frequency, what is phase crossover frequency. From that information we can define what is gain margin and what is phase margin, and we shall study how gain margin and phase margin can be obtained in polar plots and how it can be correlated to the gain margin and phase margin of Bode plot. So let us start with the crossover frequencies. So as we have studied earlier, let us again take a plot of GS equal to 1 by S tau 1s plus 1 into tau 2s plus 1. So for this, if I draw the polar plot, as we have already studied this in detail in the past, this is the real part of g at j omega, h at j omega. So this is for the loop transfer function, so I write here g at j omega, so g at s, h at s. So imaginary part of g at j omega, h at j omega, h at j omega. So here the polar plot for 1 by s into tau 1s plus 1 by s into tau ns into tau 2s should start from omega equal to 0 at infinity, and it should come like this. It will cross the imaginary axis and reach the origin at plus 90 degree. So we can draw with this center and radius 1 an arc which will definitely cross this plot omega equal to 0, omega tends to infinity. So at some point for a stable plant we'll get that the crossing will be in the third quadrant of the polar plot. So this point will give a length of radius 1, this is of length 1. This frequency is basically called the gain crossover frequency. So omega Cg is the denomination for this, and at this frequency the polar plot will have a magnitude of 1. As we go ahead we will reach the negative real axis, which is actually crossing of the negative real axis to give a phase of minus 180 degree. So for the phase of minus 180 degree, this is actually angle minus 180 degree, this angle is minus 180 degree. So the frequency at this point is called omega crossover phase. So omega crossover phase is phase crossover frequency for the polar plot. So these are the two frequencies where we find that the system has specific importance, that is the gain crossover frequency and phase crossover frequency. So the same plot, if we draw on simulograph paper for Bode, then we will see that the point where 0 decibel line is crossed is called the gain crossover frequency point, and a point when the phase of minus 180 degrees crossed is called the phase crossover frequency points. So with this understanding, let us go ahead. This point where the phase crossover frequency, we get some magnitude of the polar plot, we denote it by A. It will help us in determining the gain margin, and for this frequency we will get the phase margin. So let us see how. So we start with gain margin. So as we have seen that on the polar plot we have crossing like this, and this magnitude is A. So here we can say that the gain margin of a stable system can be defined as the factor at the phase crossover frequency by which the magnitude, which is less than 1 for a polar plot, for a stable plot, by which the magnitude of the stable loop transfer function can be raised to drive it to the verge of sustained oscillation or instability. Means this is the arc of this arc of radius 1. So this is actually the margin by which the gain can be raised so that the line of sustained stability or line of instability is obtained. So I am redefining the definition for you. Definition is, it is the factor at phase crossover frequency by which magnitude which is less than 1 for a stable plant, magnitude of the stable loop transfer function can be raised to drive it to the verge of sustained oscillation or instability. Sustained oscillation or instability. So as we are discussing this magnitude of A here up to the crossover frequency, so let magnitude of loop transfer function equals to A, then gain margin equals to 20 log base 10 1 by A. This is in decibels. So this should be equal to minus 20 log base 10 A in decibels. So therefore A equal to 10 power minus gain margin by 20. So you can understand that smaller is the value of A. A is less than 1 definitely, but smaller is the value of A, then higher will be the relative stability of the system. Higher will be the relative stability, because smaller is the value of A, the system will be away from the minus 1 point. If the system crosses, if it increases and crosses minus 1 point at phase crossover frequency, then definitely the system is unstable. So similarly, let us understand what is the phase margin. So as we have seen earlier, this is the plot, and you are drawing a radius of 1 is crossed at this point, omega crossover gain, gain crossover frequency. So this magnitude is definitely 1. This magnitude is 1. So we can understand that if the value of gain increases, so naturally this will shift upwards like this, and in that case this angle will keep on reducing, this angle will keep on reducing. So this is basically the angle of the phase margin, how much margin you have before the system reaches the verge of instability. So phase margin is the amount of additional phase lag of a stable loop transfer function that will drive the system model to the verge of sustained oscillation or instability. So this is the additional amount of phase which is keeping the system away from the point of or verge of instability. So I can define it as phase margin is defined as it is the amount of additional phase lag of a stable loop transfer function that will drive the system model, I mean the transfer function, to the verge of sustained oscillation or instability So mathematically we can define phase margin as angle of G at G omega, H at G omega plus 180 degree. What is this G at G omega, H at G omega plus 180 degree? Means if you are taking the angle of this plot, in the negative direction, so this at the gain crossover frequency, this angle is something a negative value but less than 180 degree. So if I am adding this value which is negative but less than 180 degree to plus 180 degree, so naturally this phase margin will be greater than 0. This will be positive until and unless this gain is increased and this unity crossing point reaches the second quadrant like this, then this angle will become negative. So for a stable system we can say certain things or certain points about phase margin and gain margin. Let us write down those points one by one. Point number one, for a stable system, gain margin and phase margin are positive. Number second, for large gain margin and phase margin, the system is stable. The system is definitely stable but sluggish. Number third point is a gain margin close to unity or a phase margin close to 0 corresponds to a highly oscillatory system. So let me write it: a gain margin close to unity or a phase margin close to 0 corresponds to a highly oscillatory system transfer function. Let us draw the polar plot for gain margin and phase margin. So I am drawing the polar plot for the same. This one, so this is the point of -1, so the same one I take the radius. So this arc is, this is omega crossover gain, and this length is definitely 1. So from here we can see that this frequency is omega crossover phase, so phase crossover frequency. So here from the value of this gain A, I can obtain how much we are away from this point of instability. Similarly here, by the value of this angle, which is the phase margin, we can obtain how much the system is away from the verge of instability. So this will help us in getting the gain margin, and this will help us in getting the phase margin. Let us try the same on Bode plot. One thing very important I like to mention at this verge of time, that here we are starting from omega equal to 0, and here we are reaching at omega tends to infinity. So gain crossover frequency is a lower frequency than phase crossover frequency for a stable system. Stable system. It is easy to draw and obtain gain margin and phase margin for polar plot, but when we draw the Bode plot, we have to be little careful, and we should use this knowledge while drawing the Bode plot. Let us see how the Bode plot will come for this. Suppose I am taking phase over here. Suppose I am taking the 0 decibel line over here, 0 decibel line over here. So I take -20 decibel, and here -40 decibel, and here 20 decibel, and here 40 decibel. So this is the point of -10 power -1, this is 10 power 0, this is 10 power 1, 10 power 2. Why we should take the normalized frequency along the x-axis we have discussed already. So we can take omega by omega n in radians per second by radians per second. So this is unitless. So this is equal to u. Now suppose I am trying to draw the Bode plot. So as we have discussed that it is the gain crossover frequency which comes first. So we see the 0 decibel line over here. So this is the 0 decibel line. Maybe assume that 10 power 0 is the gain crossover frequency. So some plot is coming like this, and then this is crossing the 0 decibel line like this and moving like this. So here we have to compare the two plots, because I got the gain crossover frequency, omega crossover gain over here, but for gain crossover frequency I have to determine the phase margin. So I have to go to the phase plot. Let us see how we can go to the phase plot. So this is the phase plot. So let us assume that this is minus 180 degree line, this is minus 180 degree line, this is minus 90 degree line, this is 0, this is minus 360 degree line. So this line will give us the phase crossover frequency somewhere after the gain crossover frequency. So maybe I take here, or I take here phase crossover frequency. So this is 10 power 0, this is 2, this is 3. Now here I am getting the omega crossover phase. So suppose some phase is changing like this, phase changes like this, suppose it is going like this. So in that case you see that at gain crossover frequency, how much is the plot away from the minus 180 degree. So this is basically giving us the phase margin of on the Bode phase plot, because at the gain crossover frequency, how much you are away from the verge of instability will be obtained by this, because more the plot is away from the minus 180 degree line, better is your relative stability. Similarly, for phase crossover frequency, we see that how much gain is away from the 0 decibel line. So this much is your gain margin. This much is your gain margin. This is an example, not a practical situation. In practical situation, it may be different. So we can obtain the gain margin and phase margin in this way. So drawing Bode plot and getting gain margin and phase margin is relatively easy if we are careful about the gain crossover frequency and phase crossover frequency. And for understanding, it will be easy to understand or explain the things using the polar plot. So this is all about gain margin and phase margin, and we learned how gain margin and phase margin can be obtained from Bode plot and polar plot. So we see that in this case both gain margin and phase margin are positive. So this much is for today, and in the next lecture we shall learn few more concepts about frequency domain studies. So this is the book I always suggest, as the language is easy, by Professor M. Gopal. One can refer to. Some more reference books are available here. And if this video is useful, please like the video and subscribe the channel to stay in contact. Thank you for your patient listening.